Hi everyone. In this video, we're gonna discuss a new and an interesting problem. I saw this problem in a mathematical statistics book by Casella and Berger. So this is what the problem says. So let's say A and B arrive at a bus stop randomly between 7 a.m. and 10 a.m. and that two independent of each other. So what you need to find out is the probability that A does not wait for B and so that's one part, and the other part is that find out the probability that A waits for about an hour for B. All right. And as we'll see later, that this is not a very good question to ask. Okay. So maybe I'll modify this to say that, waits for about an hour. Okay. Uh, and not exactly for an hour. All right. So, and assume that A does not wait for B when it arrives at the same time as B or before B. All right. So let's take an example to understand what the problem is saying. So let's say, the start and the end are 7 a.m. and 10 a.m. This is what the question statement also states. All right. So this start and end is just so that it represents that, your A and B will not be arriving at the bus stop like outside this range. All right. Now let's say, A arrives at 7:50 a.m. This is represented by TA, and B arrives at 9 a.m. That is represented by TB, right? So how much time does A have to wait for B? Then it's waiting for an hour and 10 minutes, right? Because that the gap between TA and TB is that of 1 hour and 9 and 10 minutes. All right. Let's see another example. So again, your S and E are 7 a.m. and 10 a.m. respectively. A arrives at 9 a.m., but B actually arrived before A at 8 a.m. So how much time do you think A waited for B? The wait, A did not really wait for B at all, and the wait was actually just 0. All right. So here you can pause the video and also, think of have a stab at this problem and, see, where you can progress. All right. So now let's discuss the solution. Actually, although I've written the solution here, but what we are discussing is not really the solution. Okay. All that we'll be doing is seeing, we'll be setting up our goal. All right. What is it that we want to calculate? All right. And we'll be solving and this is all part of a methodology. All right. So, which is a general framework in many probability and the stats questions that you're going to see is that, what you begin with is setting up a goal, because the problem that you have will almost always sounds horrible. It's complicated. All right. So the first step that you need to do is make it clear that what is it that you want to calculate mathematically, because remember that probability stats is full of puzzles. Okay. If you work on intuitions, very likely you will fail. All right. So that's why it's important that you do whatever you're calculating rigorously. All right. So that is why it's very important to keep in mind the methodology. All right. So again, the first step in your methodology should be to write down your goal mathematically. All right. So let's see. So okay, all that I'll be discussing right now is what the goal is. All right, and then I'll just leave it for you to find out how you can solve that goal. All right. So yeah, okay, and that's the first step, which is mathematically formulating the question. All right. So the first step is to basically write down mathematical notations and formulations for all the random variables that you can see, right? So let's say TA and TB denotes the random variables for the arrival time of A and B respectively. All right. So how can you define W? Okay, remember W is a random variable, and it is nothing but the time that A is waiting for B, and we know that this is going to be TB minus TA if A arrived before B, and this is the notation that we use for to denote that the event A happened before event B. We use a curly arrow going from A to B, which denotes that event A happened before event B. All right. So if event A happened before event B, then the weight is TB minus TA, right? And this is just following from the question. And again, as follows from the question, in other situations, when A arrived at the same time as B or after B, then the weight is for A is 0. All right. So that's what it is. And what's the goal? So the goal over here is to find out the probability that W is some value sigma. All right. But before we proceed, we also need to stop and think if the goal that we want to calculate is even reasonable at all. So remember that your TA and TB are continuous random variables, and that means is that the probability that W is going to be some specific value sigma is going to be what? It's 0. Okay, mostly. All right, and we'll see that why I wrote mostly here. But as is the case with all continuous random variables, it's almost always the case that the probability that the random variable is going to be some specific value is 0, right? So almost always it's not a reasonable question to even ask, or it's not even a reasonable goal, okay, that you are finding out the probability. So what do you think is the reasonable goal here? So the reasonable goal here should be to calculate the probability density instead. All right. um, but before that, let's actually look at, let's move on to a certain digression and see that why did I say that mostly? Why did I use that term mostly? All right. So here's the digression. Okay. So note that, I use mostly here because it turns out that for W equals to 0, okay, for that particular event, the probability is actually not 0. Okay. And in fact, it's actually exactly half. All right. um so, and the reason is this. Okay, so if you think about it, then because A and B are independent of each other, number one, and yeah, and mostly that. Okay, because A and B are independently of each other and they are identically distributed, because remember that both A and B are uniform in this range. So it indeed is the case, and that the probability that of the event that A happened before B, or A arrives at the bus stop before B, should exactly be equal to the probability that B arrived at the bus stop before A, right? They should be equally likely. All right. Or in other words, in the notations of probability, these two events should be disjunct, right? And the event that A and B arrived at the same time at the bus stop, or in other words, TA is equal to TB, is also another event, is also another possible event, but the probability of that should be 0. Okay, and you should think about it why. But the short answer is that, again, because TA and TB are both continuous random variables. Okay, so it's highly unlikely to the point that the probability should be 0, or the case that TA is exactly equal to TB. It's as simple as that. Okay, and we know and now we know that what follows is that because these three events, right, that A happened before B happened before A, and A and B happened together or arrived together at the bus stop, because these three are disjoint events, and they the union of these three events is your complete sample space. That's why we know that the probability altogether should be 1, and that's why that implies that the probability that A happened before B, or A arrived at the bus stop before B, should be exactly half. Okay, so that's what the digression was. Now let's come back. Okay, so as we were discussing earlier, that that finding out the probability that W is exactly sigma is not a reasonable goal. Instead, what should be calculating for is the probability density. So indeed, that's what you want to calculate. And mathematically, how we'll denote this probability density is using small f, small letter f, sub W. Okay, so this subscript just denotes that what random variable are we interested in, which random variable are we interested in, of finding out the probability density. Okay, so the probability, okay, and this is a very complicated looking notation, but all that we are saying is that f sub W, which means the probability density of the random variable W, evaluated at W equals to sigma. Okay, so what do you think this should be? Okay, because this is something that we want to calculate. Okay, but remember that mostly this means nothing. Okay, if we cannot express it in terms of things that make sense to us. Okay, so for example, something that makes sense to us is the probability. Okay, so how can we express this term in terms of the probability, right? So this should be equal to the probability that W lies between sigma and sigma plus D sigma, because remember, W is a continuous random variable. But is this right? No. Okay, this definition is not right. Okay, what we have to do is we'll have to divide this thing by the width of this event. Okay, so the width of this event is D sigma. So this is something that we'll have to divide it with. But again, we are not done. Okay, this is not wrong, but this is quite incomplete. The reason this is incomplete is because we are looking for something like density function. Okay, so density function is a little more sophisticated than this. Okay, and the sophistication lies in saying that the D sigma here tends to 0. Okay, so we need to evaluate this in the limit that the width tends to 0. Okay, now if you may wonder that how did this come about, then the answer is quite simple, because you know uh, we know that, for example, for any random variable x, the probability that x lies in the range a to b can actually be written as this, right? Which is, if you integrate over the density function of x from the range a and b. Okay, from the range a to b. Okay, so if you do this integration, this is going to give you the probability, although even this statement has some ifs and buts. For example, a have to be less than b. Okay, but anyways, this is what you definitely would have seen in your undergrad probability and stats course. So yes, okay. So indeed, just using this formula, we can derive the earlier thing, right? Because all that we have to note is that the interval that now we are interested in, like for example, the b over here is actually nothing but a plus dx. Okay, so if you replace b with a plus dx, right? So your integration in the limits of integration will change from a to a plus dx, and because dx is tending to 0, that's why this integration is actually going to be this integration is actually going to be nothing but the the product of the probability density and dx. Okay, so that is why we can write down this particular thing that you are seeing, that the density function is the ratio of the probability and the width uh, under the condition that the width is tending to 0. All right, so here's where I will end the video, and I'll let you think about the solution, and in the next video you can see what my approach is, and compare with yours. Thank you and best of luck.